Lab 8 Alarm Register. The goal of this exercise is to create a loadable register process to store the alarm time of the clock. In the final alarm clock design, we would need a register to store the alarm time. The alarm register component serves this purpose. The alarm register is a simple register configuration that either retains its existing value or loads a new value. The functionality is as follows. If the control signal load underscore A is 1, the input set underscore data is stored in the register. Otherwise, the current value of alarm underscore data is retained in the register. Reset is asynchronous and active low. The register is clocked on the rising edge of the clock. Alarm underscore data and set underscore data are all 4-bit standard logic vector arrays.
Create a new file called alarm underscore reg.vht containing an entity called alarm underscore reg and architecture called RTL. We see that the port list consists of clock, reset, set underscore data, and load underscore A as inputs and alarm underscore data as output. To successfully create a registered process requires you to follow a strict coding style. The easiest way to implement a loadable register is to use synchronous feedback. Therefore, you will need to use a process with the following structure. Since reset is asynchronous here, it is part of the sensitivity list of the process. If reset is low, then we assign the reset value to the output. Else if on rising edge of the clock, we need to load a new value onto the output. This completes the design. We shall now code the test bench. Create a file t underscore alarm underscore reg.vht. Declare the library and the package. Declare an entity with empty port list as nothing goes in or comes out of the test bench. Create an architecture test of entity t underscore alarm reg. We declare the component alarm underscore reg along with its port list. Declare all the local signals to connect the DUT to the test bench. We instantiate the alarm reg component. Since we intend to infer a sequential logic, we generate a clock. For this, we initialize the clock with 0 and then negate it every half period using a concurrent assignment statement. In process stimulus, we first apply reset and check if alarm underscore data is set to 00. Next, we drive high on the signal load underscore A to check if alarm underscore data is driven with set underscore data. With load underscore A low, we drive set underscore data with 1111 to ensure that the output alarm underscore data is unaffected by the new value of set underscore data and retains its old value. We again drive load underscore A high and set underscore data with all zeros to check if the output alarm underscore data is all zeros. Next, we drive load underscore A with 0 and set underscore data with 1010 and see that the alarm underscore data is unaffected by the new value of set underscore data. Since we have clock running infinitely, the report statement here halts the simulation. Execute the xrun command along with -v2000x option to enable the use of report statement. Right-click on the top file. Select Send to Waveform window from the drop-down menu. Run the simulation. Adjust the time scale to view the output conveniently. We see in the test bench that we drive the stimulus for 7 clock periods and hence we have the simulation running up to 70 nanoseconds as each clock period is 10 nanoseconds. In the waveform, we see that until 20 nanoseconds, output is uninitialized At 20 nanoseconds, the reset goes low and hence the output alarm underscore data is assigned with 0000. We see that we have applied inputs on neck edge of the clock and the output is to be observed on the pause edge of the clock. At 30 nanosecond, reset is driven low and load underscore hey goes high, ends at the next pause edge. Alarm underscore data must be assigned with the new value of set underscore data, which is 5. At 45 nanosecond, we see that reset is disabled and load underscore A is 0. Hence, alarm underscore data should retain its old value, which is 5, and not be affected with the new value of set underscore data. And so on. This verifies the functionality of the design. Let us synthesize the design. Change the design variable to alarm underscore register. Since this is a sequential circuit that uses clock, we need to specify the clock and input and output delay constraints. Let us invoke the tool by executing the genus command. View the output in the schematic pane. We see that the generated netlist as clock, reset, set underscore data and load underscore A as inputs and 4-bit alarm underscore data as output, and we also have 4 D flip-flops and 4 multiplexers, one for each bit of the 4-bit standard logic vector array. This completes this lab.